So as of now, we have discussed the Newton's first law and the second law. Now we're going to explore the free body diagrams and why these diagrams are important. Because while solving problems involving forces and Newton's law, it is very useful to make a sketch that indicates every external force acting on a body. And we call this sketch a free body diagram. And for the time being, we will not consider the rotational motion of object, and also will treat the object as the point object. Okay, now let's try to make the free body diagram of sofa. So here you see a person applying a force on sofa. Now to make the free body diagram, there are 4 basic steps. The first step is indicate all the external forces acting on the object of interest. Here our object of interest is this sofa. So the first force that acts on the sofa is due to this person. Let this force be F, right? Next, the gravity also exerts a force on sofa. So let this force be W. Basically this would be the weight of chair. And finally the normal force exerted by the floor on the sofa, and it is in the upward direction N. And this normal force prevents the sofa from falling towards the center of earth. And why we call it a normal force? Because it is perpendicular to the surface. Now next step is to isolate the object of interest and replace the object with a point particle of same mass. So we have isolated the object and we have considered a point mass, and we have shown all the forces acting on that point. So this is the second step. Now next step is to define the coordinate system. So you can choose any coordinate system according to your convenient, but if you know the direction in which the object is moving, you can take that direction to be one of the coordinate axes, or you can take a coordinate system that aligns with one or more forces acting on the object. So in this case, let us take this to be the coordinate system. So this is our coordinate system. This is positive x and this is positive y. And the final step is to resolve the forces into components, right? So this angle, let this be theta. Now there are 3 forces acting. The first force, we have the force F. So along the x direction, the component would be F cosine theta, and along the y direction we have minus F sine theta. And why this is minus? Because it is along the negative y. Then for the second force, normal force, Nx, this is 0 because there is no component along the x direction, and Ny we have equals to N. Finally the weight force, Wx is 0 and Wy we have minus W. So we have resolved all the forces into components. So these are the basic 4 steps to draw the free body diagram. Now let's try to apply the Newton's second law of motion for one-dimensional systems. Okay, so here you see a person holding a football at rest. Now think how much force is needed to keep the ball from falling down. You may say that the force needed would be equal to the weight of football. Now let's verify this by using the Newton's second law. So first we'll sketch the free body diagram. So we're going to isolate this football and replace it with a point object. So this is the point object, and now the forces acting on it. First we have the gravity force in the downward direction, this is W. Then the upward force applied by your hand onto the football, so this is the normal force N. Now next, the coordinate system. So this is our coordinate system. This is positive x and positive y. Now let's try to resolve the forces into components. So Ny, this would be equals to N. Wy equals to minus W. Minus is y because it's along the negative y, and in the horizontal direction there is no component for these forces, so no need to write. Now we're going to apply the Newton's second law of motion in the vertical direction or along the y-axis. Okay, so sigma Fy equals to mass times acceleration in the y direction, right? The sum of forces we have N minus W is equals to, now acceleration in the y direction is 0, so this whole term is 0, right? So that is equals to 0, and from here this N would be equals to W. Therefore the force applied by your hand onto the football is equals to the weight of the object. and this is the same result that we expected. Now let's try to take one more example where the object of interest is accelerating. This time it was at rest. Now we'll be taking that the object of interest is accelerating. Now in this example we have three persons, Maya, Loki and Chetan, push a 752 kg boat that floats next to a dock, and they each exerts a force of 80.5 Newton parallel to dock. And we need to find what is acceleration of the boat if Loki and Chetan push in the opposite direction to Maya, that you can see in this figure also. Okay, first we're going to draw the free body diagram. So we'll replace this the object of interest by a point object. The object of interest in this case we have this boat. So this is our point object, boat. Now three forces are acting. First we have in this direction, this is the force exerted by Maya. Two more forces we have, and it is opposite to the direction of Maya. So in this direction, and this is the second force. This is Fc and this is Fl. Now we'll define the coordinate system. So this is our positive x, right? Now we're going to resolve the forces in the x direction. Now the component of force in the x direction, we have Fmx, and that is equals to 80.5 Newton, and Flx and Fcx, the component of these two forces along the x direction, this would be minus 80.5 Newton because it is along the negative x, right? Now apply the Newton's second law of motion. So sigma Fx, this is equals to acceleration in the x direction times m, or we can write that the acceleration, this would be sigma Fx divided by m, right? So acceleration we need to find is equals to sigma Fx, we have this is Fmx, then plus Flx, then plus Fcx divided by m, and that would be, this is a plus 80.5, then minus 80.5, then again minus 80.5 divided by mass. Mass we are given to be 752 kgs. So this would be 752 kgs, and from here we can easily find the acceleration, and that comes out to be as negative 0.107 meter per second squared. Negative sign denotes that the acceleration is along the negative x. So this is the way we solve the problems by using the Newton's second law of motion. Now in certain problems we have to first calculate the acceleration of object using kinematic equations that we studied in chapter 2 and chapter 4, and then we have to use the Newton's second law to find the net force that caused the acceleration. Let's see a real world problem based on this. So this runway is made up of Foamcrete. Now Foamcrete is a substance designed to stop an airplane. This Foamcrete is solid enough to support a car, but it crumbles under the weight of a large airplane, and by crumbling, Foamcrete slows the plane to a safe stop. Now let's take an example on it. So this is an example, and it says that we have a jetliner with a mass of 1.75 times 10 to the power 5 kgs and an initial speed of 26.8 meter per second. So here the jetliner has an initial speed of 26.8 meter per second, and it is stopped within a distance of 122 meters. So this delta x we have 122 meters, and here the final velocity becomes. Now we need to find the magnitude of the retarding force exerted by the Foamcrete on the plane. Okay, so first we're going to find the acceleration, and then we're going to apply the Newton's second law to find the force, the retarding force. Okay, to calculate the acceleration, we're going to apply the kinematic equations that we studied in chapter 2 and 4. So this is the positive x direction. So Vx square is equals to V naught square plus 2 times Ax times delta x, right? Now V naught is the initial speed, which is 26.8. Final speed becomes 0. So this is the final speed, it's 0. And V naught we have 26.8 meter per second and its whole square plus 2 times acceleration that we need to find in the x direction times delta x is 122 meters. Now from here ax, it comes out to be as negative 2.94 meter per second squared. So acceleration is negative means the acceleration is along the negative x. Now we're going to apply the Newton's second law of motion, but before that we're going to make a free body diagram for this for the jetliner. So this is the point mass. Now force is along this direction, this is F, and we have taken this direction to be the positive x. So in the x direction, sigma fx, we have the component of force. In the x direction we have minus F. Now by applying the Newton's second law, we can write that sigma fx is equals to mass times acceleration in the x direction, and sigma fx we have minus F is equals to mass as it is acceleration in the x direction, we have minus 2.94 meter per second squared. From here we can find the force. Now from here F would be equals to mass times acceleration. So mass we have for the aircraft, we are given to be 1.75 times 10 to the power 5. So 1.75 times 10 to the power 5. This is kg. Acceleration is 2.94 meter per second squared. Now from here the retarding force, this is basically the magnitude. It comes out to be as 5.15 times 10 to the power 5 Newton. And if you wish to write the force in the vector form, so this force would be equals to minus 5.15 times 10 to the power 5 x cap, and the unit would be in Newton. So this would be the required answer.